When people ask me, what if the moon is not natural? I hear two different questions hiding inside one sentence. The first is about the moon itself. Is it an artificial object? Could some advanced civilization have built it or moved it? The second is deeper. It asks what it would mean for our understanding of gravity, space-time, and the universe if something as familiar as the moon turned out to be fundamentally different from what we think. I want to follow both of these threads, but I will stay grounded in real physics. No invented facts, no hidden alien engineering, just a careful look at what we know, how we know it, and what it would take to overturn that knowledge. I will start with the very basic point. In modern astrophysics, the moon is a natural satellite. All the evidence we have supports this. Its orbit, its composition, its age, its internal structure, and its formation history all fit into our broader understanding of how planets and moons form in a universe governed by gravity and the known laws of physics. But the interesting part is not just the conclusion. It is the chain of reasoning that leads there, and what that reasoning tells us about gravity, dark matter, dark energy, and the fate of structures like the Earth-Moon system in an expanding universe. The moon orbits Earth because of gravity. In Einstein's theory, gravity is not a force pulling at a distance in the old Newtonian sense. It is the curvature of space-time caused by mass and energy. The Earth curves space-time around it. The moon moves along a path in that curved space-time that we see as an orbit. We can describe that orbit very precisely with Newton's laws for most purposes, but underneath, it is general relativity doing the work. We test this constantly. We track the moon's position with radar, lasers, and spacecraft. We bounce laser pulses off retroreflectors placed on the moon by Apollo astronauts and Soviet landers. We measure the round-trip travel time to within a few millimeters. These measurements show that the moon's orbit evolves exactly as expected from tidal interactions and general relativity. There are no unexplained forces, no hidden mass, no anomalies that would suggest the moon is anything other than a big rock obeying the same laws as everything else. If the moon were not natural in the strong sense, for example, if it were a hollow megastructure with exotic mass distribution or propulsion, we would see that in the dynamics. The gravitational field around Earth and the moon would not match the predictions from their observed masses and densities. The trajectories of spacecraft in cislunar space would deviate from our calculations. Lunar laser ranging would show strange changes in distance not explained by tides and orbital mechanics. But what we see is boring in the best possible way. The moon's mass is about 1/81 of Earth's. Its bulk density is about 3.3 grams per cubic centimeter, less than Earth's because it has a smaller iron core fraction. Its moment of inertia, inferred from how it spins and wobbles, matches a differentiated rocky body, not a hollow shell. The gravity field of the moon, mapped by missions like GRAIL, shows mascons, or mass concentrations, under some basins, which are dense regions of crust and mantle, not signs of artificial construction. The origin of the moon is also a test of how natural it is. The leading model is the giant impact hypothesis. Early in the solar system, about 4.5 billion years ago, a Mars-sized body, often called Theia, collided with the proto-Earth. The impact threw material from the outer layers of both bodies into orbit. That debris disk cooled and clumped into the moon. This idea is not just a story. It is supported by multiple lines of evidence. Lunar rocks brought back by Apollo and Luna missions have isotopic ratios, especially of oxygen, that are almost identical to Earth's mantle. This suggests a common origin. The moon is depleted in volatiles compared to Earth, which fits with formation from superheated debris. The angular momentum of the Earth-Moon system, how much rotational and orbital motion it has, matches what you would expect from a giant impact. Computer simulations of such impacts reproduce many of the observed properties of the moon's orbit and composition. there are still open questions about details. The isotopic similarity is so close that some versions of the giant impact need refinement. Maybe the impact was more violent. Maybe there was more mixing. Maybe multiple impacts contributed. But all of these possibilities are still fully natural. They involve gravity, collisions, and thermodynamics, not artificial engineering. To claim the moon is not natural, we would need evidence that cannot be explained by any reasonable combination of known processes. So far, we do not have that. Now let me connect this to dark matter and dark energy. At first, the moon seems like a purely local object. Why talk about the large-scale structure of the universe? The reason is that the same theory of gravity that explains the moon's orbit also underpins our interpretation of galaxies, clusters, and cosmic expansion. If something as close and precisely measured as the moon showed a real, persistent deviation from general relativity or from Newtonian gravity in the weak field limit, that would be a major clue that our theory is incomplete. Some alternative gravity theories propose to explain galaxy rotation curves without dark matter, try to modify gravity at low accelerations. The Earth-Moon system is a test bed for such ideas. We can compute the gravitational acceleration between Earth and Moon. It is much higher than the very low accelerations found at the outskirts of galaxies where dark matter effects become important. So the Moon's orbit does not probe the same regime where dark matter shows up most strongly, but we can still look for small deviations. Lunar laser ranging tests the inverse square law of gravity and the equivalence principle with high precision. If the moon's motion did not match these laws, it might point to new physics that could, in principle, change how we think about dark matter. So far, the tests say general relativity works extremely well on Earth-Moon scales. That pushes any modifications needed to explain dark matter out to different regimes or different scales. It also supports the idea that dark matter is not a failure of gravity at the scale of the moon. It is likely a real form of matter that does not emit light, present on galactic and larger scales. Dark matter itself does not play a significant role in the moon's orbit. The density of dark matter in our region of the Milky Way is very low, roughly a fraction of a proton mass per cubic centimeter, depending on the model. The gravitational influence of that amount of dark matter on the Earth-Moon system is negligible compared to the gravity of Earth and the Moon. If the Moon were an artificial object made of exotic dark matter, its mass and gravitational effects would still show up in the same way. Gravity does not care if mass is natural or artificial. It only cares about the amount and distribution of mass energy. We do not see any need for exotic matter to explain the moon. The mass inferred from its gravity matches the mass inferred from its size, density, and composition. Dark energy is even more remote from the moon's everyday behavior. Dark energy is the name we give to the cause of the observed accelerated expansion of the universe. On the largest scales, space itself is expanding, and that expansion is speeding up. We infer dark energy from observations of distant supernovae, from the cosmic microwave background, and from large-scale structure. In the simplest model, dark energy is a cosmological constant, a constant energy density of empty space. This energy density is tiny on local scales, but because it is uniform and fills space, it dominates the energy budget of the universe on the largest scales. The key point is that dark energy does not tear apart bound systems like the Earth-Moon system. Gravity at small scales is much stronger than the very gentle effect of cosmic expansion. In general relativity, a gravitationally bound system is decoupled from the Hubble expansion. The space between Earth and Moon is not stretching in the same way as the space between distant galaxies. The Moon is not drifting away because of dark energy. It is drifting away because of tidal interactions. Tides transfer angular momentum from Earth's rotation to the Moon's orbit. Earth's rotation slows down. The Moon's orbit expands. We measure this recession at about 3.8 centimeters per year. Lunar laser ranging confirms this. The rate matches what we expect from tidal theory and from geological records of ancient day lengths and tidal patterns. No dark energy is needed to explain it. Thinking about the moon's recession, though, does connect us to the fate of the Earth-Moon system and to the distant future of the universe. If we project forward, the moon will continue to move away until Earth and moon become tidally locked to each other. One day, very far in the future, if the sun did not interfere, Earth would always show the same face to the moon, and the day length would match the moon's orbital period. But the sun will interfere. In about 5 billion years, the sun will evolve into a red giant. Long before that, changes in solar luminosity will transform Earth's climate. The Earth-Moon system will not reach double tidal locking in its current form. The sun's evolution will dominate. The moon will almost certainly remain a natural satellite throughout this entire story. There is no role for artificial engineering here in our current understanding. On even larger scales, dark energy controls the long-term fate of cosmic structures. In the standard LIL-CDM model, where LIL is the cosmological constant and CDM is cold dark matter, the universe will expand forever. Galaxies not gravitationally bound to us will recede beyond our cosmic horizon. The local group of galaxies, including the Milky Way and Andromeda, will eventually merge into a large elliptical galaxy. Inside that remnant, gravity will still bind stars and planets and moons. Dark energy will not unbind them. So in that future, if any moons still orbit planets, they will still be governed by the same local gravity that holds the moon around Earth today. The cosmic expansion will continue outside, but local spacetime curvature from mass will still dominate on small scales. If we imagine as a thought experiment that the moon were not natural but was placed in orbit by some advanced civilization, we can ask what that would change in our physics. The answer is not much, unless the moon's internal physics were also exotic. An engineered object could still be made of ordinary rock and metal. It would still obey general relativity. It would still curve space-time according to its mass energy. It would still follow geodesics, the natural paths in curved space-time, unless it used propulsion to counteract them. Our equations for orbits would still work. Our measurements of gravity would still match. From the point of view of gravity and cosmology, an artificial moon made of ordinary matter is indistinguishable from a natural moon with the same mass and shape, as long as it is not actively pushing itself around. To detect artificiality, we would need non-gravitational evidence. For example, unusual materials, internal structures inconsistent with geological processes, or ongoing energy use. Seismometers placed on the moon during Apollo measured moonquakes and impacts. The way seismic waves travel through the moon tells us about its interior. They show a solid crust, a partially molten boundary layer, and a small core. The data are noisy and incomplete, but they are consistent with a natural differentiated body. There is no sign of large hollow cavities or engineered frameworks at the scale we could detect. The moon also has a history of impact craters, volcanic activity, and regolith formation that fits with billions of years of natural evolution in the inner solar system. So, from the standpoint of evidence, the moon looks very natural. But the question, what if it is not, pushes us to think about how robust our physical theories are. Gravity is tested across many scales. On Earth in the lab with torsion balances and atomic clocks, in the solar system with planetary orbits, spacecraft trajectories, and lunar laser ranging. In strong fields with binary pulsars and black holes, on galactic scales with rotation curves and gravitational lensing, on cosmological scales with the expansion history and the cosmic microwave background. The same underlying theory, general relativity, plus dark matter and dark energy, ties all of these together. If the moon's behavior did not fit, we would be forced to adjust that theory in a way that still explains all the other data. That is a high bar. There are some speculative ideas in the literature about modified gravity instead of dark matter, or dynamic dark energy instead of a cosmological constant. But none of these mainstream ideas rely on the moon being special or artificial. The moon is one more data point that supports the current framework. Its orbit helps constrain deviations from the inverse square law. Its motion helps test whether the gravitational constant g changes over time. Measurements show that any variation is extremely small. Its existence and properties fit into models of planet formation that we also apply to exomoons and exoplanets. Let me connect this to large-scale structure. The universe is not just stars and planets. It has a cosmic web of dark matter and gas, with galaxies forming in dense regions. We infer the presence of dark matter because the visible matter alone cannot explain the gravitational binding of galaxies and clusters. We see galaxies rotating too fast in their outer regions. We see gravitational lensing bending light more than visible matter can account for. We see patterns in the cosmic microwave background that require an extra component of non-baryonic matter. The moon is made of baryonic matter, the same protons and neutrons that make up us. Its mass is tiny compared to the mass of dark matter in the Milky Way halo. But the fact that its behavior matches baryonic physics and standard gravity is part of the reason we separate the problems. We do not need to modify gravity to explain the moon. We do need something extra to explain galaxies. If the moon were somehow made of dark matter, it would be almost invisible except through gravity. But dark matter, as far as we know, interacts very weakly with itself and with normal matter, mostly through gravity. It does not clump into small, dense, solid bodies easily. It forms large, diffuse halos. Simulations of structure formation with cold dark matter show that it collapses into halos and subhalos, but not into compact, rocky objects like moons. Also, if the moon were made of dark matter, we would not see the reflected sunlight, the surface rocks, the regolith, the basalt flows, or the mineral composition we measure. So the moon is not a dark matter object. It is a standard baryonic body embedded in a dark matter halo on galactic scales. When we talk about the moon in spacetime, we also have to mention frame dragging and tiny relativistic effects. Earth's rotation slightly drags spacetime around it, an effect called the lens-Thirring effect. This has been measured with satellites like Gravity Probe B and with laser ranging of geodetic satellites. The effect is small, but real. The moon's orbit includes such relativistic corrections, and our models that include general relativity match the data. If the moon's mass distribution were very strange, or if there were some exotic space-time structure associated with it, we might see anomalies in these precision tests. We do not. The cosmic expansion itself is described by solutions to Einstein's equations, like the Friedmann-Lemaitre-Robertson-Walker metric. These solutions assume the universe is homogeneous and isotropic on large scales. On small scales, like the Earth-Moon distance, this symmetry breaks down. Local overdensities of matter create their own curvature. The moon lives in the curved space-time well of Earth and the Sun, not in the smooth, expanding background. This separation of scales is why cosmic expansion does not pull the moon away. It is also why we can talk about the moon's dynamics without constantly referencing the expansion of the universe. But at a conceptual level, it is all one theory. The same equations describe both regimes, just with different approximations. In the far future, as dark energy continues to dominate, the observable universe will shrink in a practical sense. Distant galaxies will redshift away, their light stretched to longer and longer wavelengths, eventually beyond detectability. Any future observers in our local group remnant will see a much emptier sky. If they look at their own moons and planets, they will have to reconstruct cosmology largely from local physics, because the external evidence will be gone. They might measure orbits, gravity, and local spacetime curvature, just as we do with the moon. From that, they could, in principle, infer general relativity. But without the cosmic microwave background or distant galaxies, it would be harder to discover dark energy. Our current era is special in that we can see both local and cosmological scales clearly. So when I am asked, what if the moon is not natural? I treat it as a challenge to show how deeply interconnected our understanding is. To make the moon artificial in a way that matters to cosmology, you would need to break or modify general relativity, or introduce new forms of matter or energy with strange properties. Those changes would ripple outward. They would affect how we interpret galaxy rotation curves, gravitational lensing, the expansion history of the universe, and the cosmic microwave background. They would force us to rebuild the LCDM model. That is not impossible in principle. Science is always open to revision. But the bar is high, and the evidence from the moon does not push us in that direction. Instead, the moon serves as a nearby laboratory where we test gravity with exquisite precision. It helps us confirm that the same space-time geometry that describes the bending of light around galaxies and the redshift of distant supernovae also describes the monthly dance of a rocky satellite around a terrestrial planet. It reminds us that dark matter and dark energy, though invisible and mysterious, are constrained by a framework that must work on all scales, from the sub-millimeter lab experiment to the cosmic horizon. We still have many open questions. We do not know the exact particle nature of dark matter. We do not know whether dark energy is truly a cosmological constant or something that changes over time. We do not know the full details of the moon's formation, down to each impact and each molten ocean stage. We do not know how common large moons like ours are around Earth-like exoplanets, or how their presence affects climate and habitability over billions of years. And we do not know at a deep level why the laws of physics are what they are, and not slightly different in ways that might have given us a very different kind of universe, perhaps one without stable moons at all. So I will end with one specific, unresolved mystery that ties the moon to the larger cosmos. We know that dark energy drives the accelerated expansion of the universe. We model it as a constant vacuum energy density, but when we try to compute the vacuum energy from quantum field theory, we get a value that is enormously larger than what we observe, off by many orders of magnitude. This is the cosmological constant problem. We do not know why the vacuum energy is so small, but non-zero. That tiny energy density shapes the ultimate fate of galaxies, stars, and planets. It determines that the universe will expand forever. It sets the stage for the distant future, in which systems like the Earth-Moon pair, or their analogs, will live out their final orbits in an ever-emptier cosmos. We can describe how the moon moves through space-time today with great precision, but we still do not understand why space-time, at the deepest level, has the properties it does, including this mysterious dark energy that will decide the long-term future of every natural moon in the universe.